For 60 years, silicon has been the unquestioned foundation of every computer chip on Earth. Every phone in your pocket, every laptop on your desk, every server humming inside an AI data center owes its existence to one element on the periodic table. But silicon has a problem. As transistors shrink below 10 nanometers, the physics starts fighting back. Electrons leak, heat builds up. Performance gains get smaller and smaller, no matter how much money gets thrown at the problem. Now, a team of researchers at Peking University says they have found a way around that wall entirely, and they didn't do it by making silicon smaller. They did it by replacing silicon altogether. Their new transistor, built from a material most people have never heard of, is reported to run about 40% faster than comparable transistors from Intel, TSMC, and Samsung, while using less power. If that number holds up at scale, it would mark one of the most significant materials breakthroughs in the history of the chip industry. So what exactly did they build, and how worried should the rest of the world be? Let's break it down.
To understand why this matters, you first need to understand what silicon is actually struggling with. A transistor is essentially a tiny switch. Electrical current flows through a channel, and a gate controls whether that current is on or off. For decades, engineers made chips faster by making that channel shorter, packing more transistors into the same area. This is the essence of Moore's law. The problem is that silicon atoms only pack so tightly, and once a channel gets thin enough, silicon's own atomic structure gets in the way. Electrons scatter, current leaks through the channel even when the switch is supposed to be off. Engineers call this the short channel effect, and it's a major reason why progress below the 10 nanometer range has become brutally difficult and expensive. Think of it like trying to run water through a pipe that keeps getting narrower and rougher on the inside. Eventually, no matter how hard you push, the water starts leaking out through cracks in the pipe wall rather than flowing cleanly to the other end. Chip makers have spent billions of dollars and years of research squeezing out small improvements. But many engineers now believe silicon, as a material, is approaching its natural limit. That is exactly the gap the Peking University team decided to attack, not by refining silicon further, but by walking away from it.
The material at the center of this story has an intimidating name, bismuth-oxyselenide, written as Bi2O2Se. Paired with it is a second material, bismuth selenide oxide, or Bi2SeO5, which acts as the insulating gate layer. Both are what scientists call two-dimensional materials, meaning they can be grown in sheets only a few atoms thick, similar in spirit to graphene, but with very different electrical behavior. The research team, led by Professor Peng Hai-Lin, has actually been developing this bismuth-based material system for close to 10 years. What makes it special is how cleanly electrons move through it. In ordinary silicon oxide interfaces, tiny defects and rough atomic boundaries cause electrons to scatter, losing energy as they go, similar to water hitting rocks in a riverbed. The Peking University team engineered their bismuth-based interface to be remarkably smooth and largely free of these defects. One of the researchers described it simply: electrons flow through the material almost like water moving through a smooth pipe, with very little resistance. Less resistance means less wasted energy, lower required voltage, and faster switching speeds. The three things every chip designer on the planet is fighting to improve at the same time.
Here is where the story gets its headline. The Peking University team fabricated experimental transistors using this bismuth-based system and tested them using the school's high-precision processing platform. To validate the results, they also ran density functional theory simulations, a standard computational chemistry method used to model how electrons behave inside a material at the atomic level. According to the researchers, their transistor outperformed the most advanced comparable devices from Intel, TSMC, Samsung, and Belgium's IMEC Research Center, all tested under matching operating conditions to keep the comparison fair. The reported gain? Roughly 40% higher performance, using less power. It is worth being precise about what that claim actually covers.
This is a laboratory transistor, tested as an individual device, not a finished commercial chip running real software. But even as a single device result, a 40% jump against some of the best silicon transistors the world's top chip makers can currently produce is a serious number, not a rounding error. It signals that the bismuth material system is not just a theoretical curiosity. It behaves like a real competitor to silicon under real testing conditions.
A fast transistor sitting alone on a lab bench is one kind of achievement. Getting that same material to work inside an actual electronic circuit is a very different and much harder kind of achievement. According to the research team, they have already gone a step further, incorporating their bismuth-based transistors into prototype devices and demonstrating that the new material can integrate with existing electronic circuitry. That detail matters more than it might sound. Two-dimensional materials are notoriously difficult to manufacture at scale because they are only a few atoms thick and extremely sensitive to the surface they are grown on. Getting them to cooperate with conventional circuit elements, rather than requiring an entirely new manufacturing universe, is one of the biggest practical hurdles any new semiconductor material has to clear. The fact that this step has already been demonstrated suggests there is no fundamental physics-level barrier stopping this material from eventually being manufactured at industrial scale. That does not mean mass production is close. It means the door is not closed. To understand why this result is getting so much attention, it helps to zoom out to the bigger picture. Since 2019, the United States has restricted China's access to advanced chip-making equipment, including the extreme ultraviolet lithography machines made almost exclusively by the Dutch company ASML. Those machines are essential for manufacturing the smallest, most advanced silicon transistors used in phones, GPUs, and AI accelerators. The restrictions were designed to slow China's progress in cutting-edge computing. Instead, they appear to be pushing Chinese researchers toward a different strategy entirely. Skip the race to shrink silicon and find a new material where China can compete on its own terms, using its own equipment and its own manufacturing playbook. If a bismuth-based transistor can eventually be manufactured without needing the same ultraviolet lithography tools that silicon depends on, that would represent something more disruptive than simply catching up. It would represent a bypass, a way of stepping around the exact choke point the export restrictions were built to control. That is the real reason this story is spreading far beyond academic circles. If bismuth-based transistors eventually reach commercial maturity, the impact would not be limited to one type of device. Faster switching speeds and lower power consumption are valuable almost everywhere in modern computing. Smartphones could see longer battery life without sacrificing performance. Data centers, which already spend enormous amounts of money and electricity keeping AI servers cool and powered, could benefit from transistors that generate less waste heat while doing more work. Edge devices, small local processors used in cameras, sensors, and industrial equipment, could run more advanced AI models directly on the device rather than sending data back to the cloud. None of these outcomes are guaranteed, but they represent the range of applications that motivate serious investment in a new transistor material in the first place. A next-generation semiconductor is never interesting for one product alone. It is interesting because it can quietly upgrade the entire computing stack, from the chip inside a phone to the servers powering the next generation of artificial intelligence. None of this means silicon is finished, and it is important to say that clearly. Turning a laboratory transistor into a commercial product is one of the hardest transitions in all of engineering. The Peking University team will need to prove that their bismuth-based material can be grown consistently across large wafers, not just small experimental samples. They will need to show that manufacturing yield, the percentage of working transistors produced across a full production run, is high enough to be economically viable. They will need to demonstrate long-term reliability across millions or billions of transistors operating continuously for years, not just a handful of devices tested briefly in a lab. And they will need a fabrication process that can be scaled up using cost-effective, repeatable industrial methods, rather than the careful, hands-on techniques common in university research.
Every major semiconductor material in history, including silicon itself, has needed to go through this exact gauntlet. Some new materials never make it through. The ones that do usually take a decade or more between the first lab demonstration and the first commercial chip. This is a genuinely important result. It is not yet a finished product.
Here is how I see it. The headline number, 40% faster than Intel, is the kind of figure that grabs attention, and it should. But the more important detail buried underneath that headline is that this bismuth material system has already been in development for close to a decade, and the team has already shown it can integrate with real circuitry, not just survive as an isolated lab curiosity. That combination, a strong performance number plus an early integration demonstration, is what separates a genuine breakthrough from a flashy press release. China has not replaced silicon. Bismuth-based chips are not shipping in phones or laptops today, and years of manufacturing work stand between this lab result and anything resembling mass production. But the direction of travel is clear. Faced with restrictions designed to slow down conventional chip scaling, Chinese researchers are increasingly looking for entirely new materials rather than fighting for every last nanometer of silicon. Whether bismuth-based transistors become the next major chapter in computing or remain an impressive result confined to academic papers is still an open question, but it is no longer a question anyone in the semiconductor industry can afford to ignore. So here's the real question. Could a material almost nobody outside a physics lab had heard of a few years ago end up reshaping the global chip industry? Or will the enormous cost and difficulty of scaling brand new semiconductor materials keep silicon in charge for another decade? Let me know what you think in the comments. And if you want more grounded breakdowns of the real engineering breakthroughs coming out of China's chip and AI industry, subscribe, because the next chapter of this story is still being written, and it is not slowing down.